G'day, in this video we're going to be looking at solving some problems with the equations that we derived in our previous video for energy changes in planetary orbits. We're still focusing on dot point 5.3.5, and our key learning intentions for today are to start to familiarize ourselves with the types of calculations and problems we might get asked which are relevant to this topic. In this first question, we're being asked to qualitatively describe the energy changes required to raise a satellite from mid-Earth orbit to a geostationary orbit. So, we've got to imagine that we have a satellite, say, in this position, and we are raising it to an orbit which is geostationary. What that means is that the radius is going to increase. Now, it doesn't necessarily mean that the satellite is just going to move from here to here in a straight line, but rather it will follow some sort of arc as it spills outwards until it reaches the geostationary radius. So for any style of question like this, there are three types of energy that we should be focusing on. That's the total energy of the satellite, the gravitational potential energy, and the kinetic energy. The position of a satellite will consequently have an effect on all three of those variables. Let's consider each. The first conclusion that we make is that if we are going to raise the orbit of a satellite and increase its radius, we must do work on the satellite so that the gravitational field can be overcome. And as a result, we must input energy. And if there's an input of energy, that's going to increase the total energy of the satellite. The second thing that we can consider is potential energy. And essentially, because we are increasing the radius of this orbital path, the conclusion is that the gravitational potential energy is going to increase as well. We can talk about that conceptually. Essentially, the further we move the two objects away, the more gravitational potential energy that there will be. And finally, if the satellite's going to maintain orbit when it has moved further away from Earth, the gravitational field has decreased, meaning the centripetal force holding the satellite in orbit decreases as well. And therefore, to adjust, the velocity of the satellite must decrease so that it stays in orbit. And by extension, that means that the kinetic energy must reduce. We can observe what I have described in our solution over here in this graph, which demonstrates how kinetic energy, total energy, and potential energy change as the radius of a satellite either increases or decreases. I've also got two calculations for you today. The first one is getting us to look at changes in gravitational potential energy when we move between orbital radii. So we have a 55 kilo meteor, which is orbiting the Earth at an orbital radius of 8.5 times 10 to the 7 meters. It moves to a lower radius of 4.8 times 10 to the 7 meters, and we're being asked to calculate the change in gravitational potential energy. Now, in order to do this, the change in gravitational potential energy, we know to be the difference between the final and initial gravitational potential energies. So what we need to do is calculate for both of those potential energies and then substitute. In our data sheet, it tells us that U is equal to GMM on R. That should be negative GMM on R. We've also been given values for the radii, the mass of the orbiting object, the asteroid, and the data sheet gives us the information that we need about the mass of the Earth, as well as G, the universal gravitational constant. The radius of the Earth is not required in this question because it's already inclusive for the orbital radius given. If we were given an altitude above the surface of the Earth, we would have to add that altitude to the radius of the Earth to get the orbital radius. So in the first step, I'm going to solve for UI and UF. From there, we can take the difference between these two values, and that will give us our change in potential energy. And this should give us negative 2 times 10 to the 8 joules. In our final question for today, we are looking at escape velocity. We're being asked to calculate the escape velocity of a 6 times 10 to the negative 2 kilo tennis ball, which is being launched from the surface of the Earth. Now, it would be convenient to remember the escape velocity formula. However, we may not have that in our memory banks. The one thing that we do need to remember, regardless of whether or not we actually recall the formula, because this concept is actually quite important to questions that don't just require a plug and chug of the numbers, but we need to be running with the assumption that When we have hit the escape velocity, it's at a point where the total energy is equal to zero, meaning that the kinetic energy and the gravitational potential energy both add up to zero. In other words, this means that K is equal to negative U, meaning that we can equate a kinetic energy and negative gravitational potential energy formula to then be able to solve for V. While we're here, something that I do want to highlight is we have been given the mass of the tennis ball. However, we'll find that it is inconsequential for our escape velocity, and this escape velocity is required for an object of any mass if it's being launched from the surface of the Earth. In this solution, we're going to be substituting in G for the universal gravitation constant. Big M will be the mass of the Earth because that's where we're launching it from, and R is simply going to be the radius of the Earth because we are launching from the surface. Escape velocities on other planets then obviously would have different values because the mass of the planet and the radius of the planet would be different. And if we've substituted incorrectly, we should find that the escape velocity would be 1.1 times 10 to the 4 meters per second. And there we go. That brings us to the end of Module 5. Thank you so much for your participation throughout this module. I look forward to seeing you in some of our videos for Module 6, which is on electromagnetism. Until then, have a good one.